Okay, so let's look at this example and say, I know this is a very small number, okay, so very much less than 1, which means very much of this is in the form of the reactants and not the products, okay? So, but exactly how much product am I going to get? That's the question I want to address. And we do that by setting up what we call an ICE table. Okay, ICE is an acronym standing for the initial change and the equilibrium concentrations. Okay, so initially, the concentration of nitrogen in air, it's about 79%, which equates to about 0.035 molar. Okay, oxygen concentration in air is about 0.0081 molar. All right, and then to start out with, we're just going to say we have pure oxygen and pure nitrogen at these concentrations, and then we don't have any of the product to begin with. Okay, so the change is now, how is this going to change? Well, we don't know how it's going to change, but we do have a clue. We know that a certain amount of this, a very small amount, as is indicated by the equilibrium constant being very small, a very small amount of this will react to form the products. Okay, so when that happens, we're going to lose some, but we don't know how much, so we'll call it X. Right? We'll lose some of the nitrogen, some of the oxygen, and we'll form, so we're going to add some NO. All right, but we have to be careful because it's 1 mole of nitrogen that reacts with 1 mole of oxygen to form 2 moles of NO. So that means we need to have those same ratios in our change. All right, so this will be 2x. We'll get twice as much of that as we have of those. All right, so then that's the change to equilibrium. So at equilibrium, what we can say is whatever I've lost here, I started with 0.035 molar, and I've lost a certain unknown amount. Okay, and likewise for oxygen, I'm going to write it down here for space, 0.0081 molar, and I've lost a certain unknown amount. And then here at equilibrium, 0, and I'm adding 2x. So at equilibrium, I have a concentration of 2x. Okay, so how do I find this value for x so I can actually calculate that concentration? Well, I use my equilibrium constant. Okay, it's the product of these values here. So my NO squared, well, this is my equilibrium concentration of NO. Okay, so what I can do is say, and this is the equilibrium constant, so it's the concentrations at equilibrium. If we're not at equilibrium, we call it the quotient and we give it the symbol Q. Okay, but that's used less often. All right, so at equilibrium, our concentration for NO is 2x, but that's squared, so this will be 2x squared. And then divided by the concentration of N2 times O2. So the concentration of N2 at equilibrium, 0.035 minus X, times the oxygen, 0.0081 minus X. Right? So this, now, and I go ahead and put this equal to times 4.5 times 10 to the minus 31. All right? This, now, I have one equation, one unknown, so I can solve this for x. Okay? Now, there's a few ways we can do that. We could plug this in, we could solve this and put it in the form of a quadratic equation where we would have some certain value x squared plus some certain value times x plus some certain constant equals 0. and then we have a quadratic equation. We could put that in there. I'm not going to take the time now to go through all of that. Maybe I'll do that in another video. Okay. We have a simpler approach where we can make a simple approximation and solve based on that approximation. Okay, and then we'll check our approximation to make sure it's safe. The approximation is that compared to 0.035, our value for x is going to be very, very small. Small enough that we can ignore it, such that 0.035 minus x will still give us 0.35. Okay, so it'd be kind of like taking a 55-gallon barrel of water and subtracting 1 drop. You're not really going to notice it. Okay, so that's what we're going to say. I think this reaction, and we can have a clue based on the size of our K, because this is so small, it's telling us we're not going to get very much of this. Okay, so we expect our value here to be very small. All right, and so that's our hunch, if you will, that x will be negligible compared to 0.035. And so we can just kind of drop that out. And likewise here, we will assume it to be too small to make a difference when we subtract. Okay. Now we only do it when we're adding or subtracting, not when we're multiplying. Okay, so we just do that, and then that will simplify this quite significantly, because up on the top 2 squared is 4, so this will be 4x squared. Now it's just divided by 0.035 minus 0, okay, so that drops out, times 0.0081. Okay, so 0.035 times 0.0081, and what I end up with here on the bottom is 0.002835. Okay, now I wouldn't really need, I don't really have 4 significant figures there, I just have 2, but I'm carrying that out until we're done with the calculation to minimize rounding errors. Okay, so now you see I've made this go down to just a constant. Okay, so now I can solve this quite straightforward, in a quite straightforward way. X is going to be equal to 4.5 times 10 to the negative 31st times this value, so I can write it like this, 2835. That will clear that part out. Then I divide by 4 and take the square root. Okay, so we can do it like this. All right. So it's just a matter of plugging those values into the calculator, and what I will end up with is 5.65 times 10 to the negative 18th. Okay, so 5.65 times 10 to the negative 18th. That is my value for x. If I want to know the concentration of NO, I multiply that by 2. Okay, so concentration of NO at equilibrium is twice this amount, which amounts to, comes out to 1.1 times 10 to the negative 17th. Right? That's in molarity. Right? So you can see an extremely small value, and that is how we go about calculating the equilibrium concentrations, and we can verify our assumption extremely small in comparison with our values here. No significant difference there, but we have a tiny amount of the NO at equilibrium there.